Yay!
Yay! Okay, electric forces. Let's see how to compute these forces between a couple of charges in a pretty easy case. And at the end, we'll talk about just how insane the strength of the electric force is compared with the force that you feel every day, which is gravity. Okay, so let's say I have a box of positive charge and it's separated by some distance r from another box of positive charge. And what I want to know is, what's the force between these? You sort of know in your head that these two, because they're like charges, they're going to repel each other. But let's go through it. Let's make sure this makes sense. And then I'll show you a shortcut, how we really solve problems using a little shortcut. Okay, anyway. Okay, so here's what we do. What you do is, one box doesn't know that the other box is there, right? How could it? I mean, they don't have eyes or anything. In physics, we don't really like the idea that one thing pushes on another thing remotely with no sort of touching there, right? So all the things that we did in Physics 1 are just a little bit mysterious. Anyway, we'll come back to that idea. But the way we get around it as you go on in physics is these two things don't just affect each other because they're positive charges. That sounds kind of magical. So I'm going to tell you something only a slight bit less magical. Each charge doesn't know about the existence of the other one, but what they do know is right around their own location, they can feel the electric field. Right? It's like going outside and you don't know what the source of the wind is outside, but you do know what the wind is at your particular location, right? So if you have a sail or something like that, you pick up on the local amount of wind. So each charge can feel the local electric field. So look, for this box that's on the right, what does the electric field do to the box that's on the left? Well, that electric field is going that way. Right? It's going away from that box. So the box on the right doesn't know anything about the box on the left. All it knows is there's an electric field pointing to the right. So what happens? It feels a force, and the force is really simple. It's just its charge times the local electric field. That's it. So it just feels the local electric field and the amount of its own charge. Sometimes the way I like to think about it is that's sort of like the area of its own sail. So the more charge it has, it's sort of like a bigger sail area. So it'll feel the force more. So that's all it does, because it doesn't know if that electric field is produced by one charge or two charges that are only half as much, or a whole bunch of charges where the net field just happens to be to the right. It doesn't know anything about that. All it knows is that at its location, it sees an electric field pointing to the right. And so this equation, F is QE, just tells it how to respond to that. It feels a force equal to its charge times the local electric field. Okay. So here's what you could do. You could compute the force like this. The force is K. Say the one on the left is, it doesn't have to be this way, but let's just say it's Q1 and Q2. In just a minute, we'll just say that they're the same, but they don't have to be. They could be different amounts of charge. So the force is going to be Q2, the force of the charge of the box that's feeling the electric field, times the electric field due to 1, right? It looks like that. And so that's just going to be Q2 times K Q1 over our, let's do it this way, our vector, like that, all right, like we did for the last unit. Okay, cool. So putting all this together, this is going to be K Q1, Q2. It's the product of the charges, r cubed, r vector. Okay, no problem. In a lot of these examples, though, what's going to happen is that all we're interested in is the strength of the force between these two charges. So, I mean, look what could happen. Q1 or Q2 or both could be positive or negative. So there's a couple of signs you have to keep track of. Our vector is from the first thing to the second thing. And so right there you have a sign possibly for those vector components that you have to keep track of. So it starts to get a little bit complicated. But if it's just two objects and they're on a line, then we could make this a lot simpler, because this could be k q1 q2 over r cubed. Oops, that didn't turn out. Over r cubed. And then what's the vector, like the way that I've drawn it here, what's the vector from one to the other one? Well, it's just r, let's just call that the x direction, right? So that's just going to be r and 0 and 0. And so when I multiply all these things out, I just get a q1 q2 over r squared. And this is just in that x hat direction, right? So this is something that we're going to use quite a bit. That if all we're interested in is the strength of the force, and I sort of know that these two things are going to be repelling each other, I can just use k q1 q2 over r squared. That's just going to give me the strength of the force, and I know that I can sort of correct later for what the direction is. If they're like charges, they're going to be repelling each other. If they're opposite charges, they're going to be attracting. So this is going to be our shortcut. Now, if we had a whole bunch of charges and I wanted to figure out what the force on any one of them is, I might have to go back to this. Might have to go back to that. Or what I would recommend, since we've already done it, I would actually go back to this. Solve for the electric field due to a whole bunch of charges, and then just multiply by the Q that's there, right? Because that's what the thing is actually doing. It's just sampling the local electric field, and which you know how to calculate from last time, and then just multiply by the charge. That way you don't have so many signs to keep track of. Okay, so look at this example though. This is kind of neat how insanely strong this electric force is. Let's do a simple example. Suppose I've got a little box of positive charge, and let's say that I've got 1 gram boxes of protons. So I'm just going to put a bunch of positive little charges in a box, and I'm going to see what the repulsive force is between them. That's a 1. Okay, and their distance r apart. Here's what's going to happen. The force is so incredible that I'm going to say that r is the distance to the moon. That sounds silly. Because 1 gram, that's like a paper clip, right? So we have a paper clip's worth of protons, and then I'm going to have another paper clip on the moon. And let's calculate what the force is, just the electric force between them. Okay, first of all, what do we need to know? It's k q1 q2 over r squared. What I need to know is what those charges are, right? So here I'm going to have F is equal to k. Well, they're the same charge. They both have the same amount of charge. So k q squared over r squared. What is Q? Okay, I know the charge per proton. That's just the one amount of fundamental charge, either an electron or a proton. One's positive, one's negative. It is 1.6 times 10 to the minus 19th coulombs per proton, right? So let's see. Oh, I need to know how many protons are in a gram. Okay, so I need to know this also. 1 gram, you can look this up. Actually, let me do it the other way around. 1 proton is equal to 1.67 times 10 to the minus 27 kilograms, so minus 24 grams. Okay, so it's 1.67 times 10 to the minus 24 grams per proton. What if I flip that around? If I flip it upside down, that tells me how many protons are in a gram. So if I flip this, what I get is about 6 times 10 to the 23rd protons per gram. That's kind of neat. That number should ring a bell. That's pretty much Avogadro's number. I'm saying that's no coincidence, because Avogadro's number relates the number of nuclear particles in a gram, and a proton's a nuclear particle. So there you go. 6 times 10 to the 23rd protons per gram. So I've got 1 gram, so I have 6 times 10 to the 23rd protons. So this times 1.6 times 10 to the minus 19th coulombs per proton is going to give me, am I going to be able to write it? Yep. This is going to give me, if I multiply those two together, what do I get? About 6 times 1.6, well, that's just going to give me about 10. 10 times 10 to the 4th, or about 10 to the 5th coulombs. So that's how much charge I have in each of these boxes. 1 gram of protons is about 10 to the 5th, 100,000 coulombs. All right, so let's put this together. So the force is going to be K is 9 times 10 to the 9th. Q is 10 to the 5th squared coulombs. What is R? The distance to the moon, you could look it up. It's about 3.84 times 10 to the 8th meters squared. I gotta square the distance. All right, let's see what we got. This is going to be, let's see, 10 to the 5th squared, that's 10 to the 10th, so 9 times 10 to the 19th. Oops, 9 times 10 to the 19th. On the top, I'm going to do about, and then on the bottom, what if I square 3.84? I don't know. 4 squared is 16. This is a little less than that. I don't know. I'm just going to call it 15 times 10 to the 16th. 10 to the 8th squared is 10 to the 16th. So this looks like, oh, this is pretty easy to do. 9 over 15, that's like 0.6. Times 10 to the 3rd, or about 600 newtons. What? This is about 150 pounds of repulsion. That's crazy, right? You have, remember what the situation was. It's a paperclip. It's a paperclip's worth of protons. So if you have a paperclip on the Earth, paperclip 1 gram on the moon, you still have a repulsive force of 150 pounds. It would pick you up off the ground if you tried to hold this thing. If you weighed less than 150 pounds. Anyway, it'd be very hard to hold on to. And then, well, you got to think, how big would this box be, really? Protons are incredibly dense. If you tried to figure out the volume of this box, what you're going to get is something that's way smaller than a bacteria. So you couldn't even hold on to it. It would just shoot right through your skin. So anyway, but that's an incredible force, 150 pounds of force if you're separated from, like the Earth, all the way to the moon. Just for fun, compare this to the gravitational force. So just for fun. Compare to the gravitational force between these protons. Because here's what you might say. Let's go back and look real quick. So the electric force is repelling these two, but they both have mass, right? So it's also true that the gravitational force is that way. So they're attracting each other gravitationally, but they're repelling each other through the electric force. Which one is stronger? Well, I mean, it's sort of no contest, even just in your head, right? If you separate 2 paper clips by the distance of the Earth to the moon, you try to figure out what's the gravitational force between the paper clips. It's not much. Certainly not 150 pounds. But just for fun, let's figure it out anyway. So this is going to be, what's the gravitational force? It was G times m1, m2 over r squared. That's the magnitude of the gravitational force. So this is going to be 6.67 times 10 to the minus 11. The masses are the same. So that's going to be 10 to the minus 3 kilograms squared. And then the distance is still going to be 3.84 times 10 to the 8th squared. Let's just do that. I don't even care what the exact answer is, right? Because this is going to be teeny tiny. But let's just figure it out roughly. So this is going to be 6.67 times 10 to the minus, let's see, 10 to the minus 3 squared, 10 to the minus 6 minus 17 on top. And then on the bottom, 3.84. What do we say that? That was like 15 or something, right? So I don't know, about 15 times 10 to the minus 16. 6.67 over 15. I don't know. I don't care. It's going to be like half, right? Whatever. So this is going to be something like 0.5 times 10 to the minus 34. See, I don't care. I don't care what it is. So this is going to be on the order of 10 to the minus 35. Oh my gosh. So gravity would have something like 10 to the minus 35, 5 times 10 to the minus 35. Compare that to the electric force, which was 600. This is in newtons. 600 newtons. So the ratio is the electric force over the gravitational force. If you just take the thing we had on the other page divided by this, it's like 600 over this thing. So it's going to be something like 10 to the 36. I want to put an exclamation point there, but I don't want you to think it's a factorial because that would be nuts. But anyway, 10 to the 36 times stronger. So the electric force is insanely strong, 10 to the 36th in this case, times stronger than the gravitational force. So in all of the problems that we're going to be doing, do we have to worry, in the case of these protons, that they're actually attracting each other gravitationally? No, because we're never going to be keeping 36 decimal points. So the gravitational force is never going to enter into it, so we don't have to worry about it. So it's an interesting, quirky thing, and still sort of a mystery why the gravitational force is so weak compared to the electric force. And what's the only reason we don't feel it on an everyday scale? Because, I mean, you trip and fall down, it hurts. Gravity seems pretty strong. But it's only because the electric force is almost perfectly balanced in normal materials. The number of positive and negative particles are just about exactly balanced. So we never feel it. It's this immensely strong force that's kept closely exactly balanced by the ratio of positive and negative charges. Very cool. All right,